Hello everyone, in this video we will learn concrete mix proportioning as per IS 10262-2019 and we will do it in a simple and step-by-step manner. We will start from design stipulations and then move step by step all the way to the final mix ratio. So make sure you watch it till the end. Now, concrete mix design is the process of determining the right proportions of different ingredients so that when the concrete is produced, it has the desired strength, good workability, and adequate durability. Now, concrete mix design is very similar to cooking. Suppose we are preparing a curry. We need the right ingredients and right proportion. Similarly, in concrete, the basic ingredients are cement, water, fine aggregate, and coarse aggregate. Sometimes we also add admixtures depending on the requirement. Just like cooking, if someone likes more spicy food, we add more chili. If someone is diabetic, we avoid sugar. So ingredients must change based on the need. But the most important thing is the proportion. If the proportion is wrong, the taste of the curry will not be good. Similarly, if the proportion of concrete is not correct, we will not get the required strength and serviceability. Now, let us first understand the design stipulations. These are the basic requirements for our mix design. We are designing M25 grade of concrete. Type of cement is PPC. Maximum nominal size of aggregate 20 mm. Zone of fine aggregate zone 1. Minimum cement content 300 kg per cubic meter. Maximum water cement ratio 0.50. Workability 75 mm slump. Exposure condition is moderate for RCC. Method of concrete placing by hand. Degree of supervision is good. Types of aggregate is crushed angular aggregates. Specific gravity of cement 3.15. Specific gravity of fine aggregate 2.65 and the specific gravity of coarse aggregate 2.85. Now, at this point, many students usually have a lot of questions. For example, what happens if the aggregate is not crushed angular? Or what if the degree of supervision is not good? Or what are the different type of exposure conditions properly mentioned in IS code? Or what if the maximum size of coarse aggregate is not 20 mm? And this type of many practical questions may come during the design of concrete mix. So, to keep this video focused and easy to follow, I have explained all this topic in detail in a separate additional video. You will find the link in the description below. And I have also added it in the I button above. So make sure you check that video as well to get a complete understanding of concrete mix design. Now, what is M25 grade of concrete? Here, M stands for mix and 25 is the characteristic compressive strength of concrete after 28 days of curing. Now, what is characteristic compressive strength? It means that if we prepare 100 number of concrete cube, then at least 95 number of concrete cube will show a strength more than 25 Newton per millimeter square if our concrete is M25 concrete. So 95% will be more than this particular value. Only 5% can be less than this particular value. So we can say that this particular value is actually 5 percentile strength value. So now, when we are preparing the concrete mix, we have one particular question. That when we are preparing the concrete mix, we will prepare the concrete mix for FCK or will we prepare the concrete mix for some higher value? And for that particular reason, we actually target our value to a higher one. And that value is known as target mean strength. Now, what is FCK? FCK is that particular value below which the result will be 5% and above which the result will be 95%. But if we prepare the result, if we prepare our concrete based on this particular value, then it may happen that 50% result will be more than FCK and 50% result will be less than FCK. So that is not our requirement. Our requirement will be such that 95% will be more than FCK and 5% will be less than FCK. And for that reason, we actually target our value to a higher value, and that is known as target mean strength. Now, normally for concrete, it actually follows one normal distribution curve, or we also say this as bell-shaped curve. Now, for other different type of particular real life problem also, normally it follows bell-shaped curve. Like if we think the height of different persons in a city like Kolkata. Now, some person will have height which is very less, and some particular person are actually very taller. So for that person, the height is very high. But actually, if we look for a particular population, most people will fall under one particular average height. So average people will be more in number. Similarly, in concrete also, target mean strength is actually the selected average target value. So if we prepare the concrete based on this average target value, 50% result will be more than that, and 50% result will be less than that. And if we prepare the concrete based on this target value, we will achieve the FCK for which 95% result will be more than that, and only 5% result will be less than that. Now, how to calculate the target mean strength? The equation is very simple. F-CK equals to FCK plus 1.65 into standard deviation. Now, from where this particular 1.65 value comes? This value is based on the normal distribution curve. Like if we set the FCK value such that 5% comes below it and 95% comes above it, then this particular value will be 1.65 into standard deviation, and this is based on the property of normal distribution curve. Now, suppose for a different problem, not for this concrete problem, suppose for a different problem, it is said that only 2% result can fail. If 2% result can fail, then 98% result must pass. At that time, this value will change from 1.65 and it will become some higher value. And that value we can get from the property of normal distribution, and there is one chart of normal distribution from which we will get this particular value. So we can calculate the target mean strength based on this particular equation, or we can calculate the target mean strength based on this particular equation also. This is F-CK equals to FCK plus X. This X is an empirical value. Now, for different problem, it may happen that standard deviation is different, but we must actually achieve one particular empirical value for all the condition. So our IS code is saying that we have to use both the equation and we have to select the higher value for calculating the target mean strength. We can also explain this particular concept of characteristic value and target value based on one simple classroom example. Suppose as a teacher, we want at least 95% of my student to pass in a particular exam, and the pass mark is 40. Now, if we tell students to just aim for 40, many of them may actually score below it. So instead, we set a higher target, say 70 marks. So what happens then? Some students may score above 70, some may score below it, but most of them still score above 40. In this way, we can ensure that about 90% student will actually pass. So the idea is simple. If we want to guarantee a minimum performance, we must always aim higher than the minimum. And this is exactly the same concept used in concrete mixed design. We do not design for the minimum strength. Instead, we design for a higher strength, higher target strength, so that most concrete samples achieve at least the required strength. So now, if data available for more than 30 samples, then standard deviation can be calculated based on this particular equation. Now, what is Xi? Xi is actually the individual test result, and X bar is actually the average of different test results. N is the number of test results, and S is the standard deviation. Standard deviation value actually tells us how much the results are varying from the average. So if suppose we have 30 number of data, and if this is the average data, then standard deviation will tell us that how much the result is deviating from the average value. Now, we can also discuss about the concept of standard deviation in these two cases. Suppose there are two categories of sample. For one category, the values, different values are 10, 8 and 12. What is the average value? 10. And suppose in a separate category, the values are 10, 6 and 14. So again the average value is 10. So for both these cases, the average value is same, which is 10. But if we go for the standard deviation, the standard deviation value is not same. If we use this simple equation and if we calculate the standard deviation, for the first case it is 2 and for the second case it is 4. Now why it is 2? Because if we just think about the mean value, the values are actually deviating by a value of 2. For the second case, if we consider the mean value, the results are deviating from the mean value by a value of 4. So here the value is more deviating, here the value is less deviating. So here we can say that standard deviation is less and here the standard deviation is more. Now what does this mean? In the first case, the values are closer to the mean, which means the results are more consistent. In the second case, the values are more spread out, which means there is more variation. And this is where quality controls become very important. Lower standard deviation means better quality control, and higher standard deviation means poor quality control. So even though the average value is same, the quality and reliability of concrete are different. It is for concrete also, it is for other cases also. If the standard deviation is more, we can say that the quality is bad and the reliability is also not proper. And this is why standard deviation plays a key role in concrete mix design. Now, if we do not have 30 test sample data, then what we can do? At that time, we have to assume the value of standard deviation from table 2. And from table 2, we know that if our grade of concrete is M25, then we have to consider the standard deviation as 4. And if our concrete is M25, we can calculate the X value from table 1. And X value will be 5.5. So we have to use both these value for calculating the value of target mean strength. Now what are the different input value? FCK is 25 Newton per millimeter square. Standard deviation is 4. And empirical value X is 5.5. So if we use the first formula, which is F-CK equals to FCK plus 1.65 into standard deviation, then we will get the result of 31.6 Newton per millimeter square. And if we use second equation, which is F-CK equals to FCK plus X, then we will get the result of 31.5 Newton per millimeter square. Now we have to compare these two results. One is 31.5, another is 31.6. So which one is more? 31.6 is more. So this will be our target mean strength. So our target mean strength will be 31.6 Newton per millimeter square. Main calculation part. Now let's understand the logic of water cement ratio versus strength. Cement needs a limited amount of water for hydration. But in practice, we usually add extra water to improve workability. Now, what happens to this extra water? After the concrete hardens, this excess water evaporates and leaves behind voids. These voids make the concrete porous and reduce its strength. So, if the water cement ratio is high, more voids are formed and strength decreases. On the other hand, if the water cement ratio is low, fewer voids are formed and the concrete becomes denser and stronger. So, the logic is very simple. Strength is inversely proportional to water cement ratio. Now, this is the graph of free water cement ratio versus 28-day compressive strength of concrete in Newton per millimeter square. Now, curve 1 is applicable for 28 days compressive strength of cement, not concrete. This is 28 days compressive strength of cement, which we normally get from mortar test. This value should be in between 33 to less than 43 Newton per millimeter square, at that time we will consider curve 1. If the value is in between 43 to less than 53, we will consider curve 2. And if the 28 days compressive strength of cement is greater than 53 Newton per millimeter square, then we will consider curve 3. In the absence of data on actual 28 days compressive strength of cement, the curves 1, 2 and 3 may be used for OPC 33, OPC 43 and OPC 53 respectively. While using PPC or PSC, the appropriate curve as per the actual strength may be utilized. In the absence of the actual 28 days compressive strength data, curve 2 may be utilized. Now for our particular problem, we know that our cement is PPC cement and we do not have any 28 days data of cement. So what we will do? We will consider curve 2 for doing our particular problem. Now in y-axis there is 28 days compressive strength of concrete. Our target strength is 31.6 and we will consider curve 2 because it is applicable for PPC when sufficient cement data is not available to us. So target value is 31.6. From this particular value, we will draw one horizontal line and it will cut curve 2 in this particular point. From this particular point, we will draw one vertical line and it will cut the x-axis in this particular point, for which the water cement ratio is 0.47. So the water cement ratio for our base trial will be 0.47. Now we have to calculate the water content for 1 meter cube of concrete. But before that, let's quickly revise one simple concept. Smaller particles have more surface area and larger particles have less surface area. Let's understand this with a simple idea. Suppose we take two bowls of aggregate, one with finer aggregate and one with coarse aggregate. And if we spread them on a table, the finer aggregate will spread more. So we can say that finer aggregates has a larger amount of surface area. And if the surface area is more water is required to wet the surface. So again, if I repeat, if the particle size is less, finer particle, then it will have more surface area. And if surface area is more water is required to wet the surface. So finer aggregate requires more amount of water. Now, if we again come back to table 4 here, you can see that with the increase in nominal maximum size of aggregate, the water content value is actually decreasing. And for our particular problem, the nominal maximum size of aggregate is 20 mm. So our water content will be 186 kg for 1 meter cube of concrete. Now, this particular water content value of 186 kg or liter, for water 1 kg equals to 1 liter. So this particular value is valid when slump value is 50 mm. But for our particular problem, we know that our slump value is not 50 mm. Our slump value is 75 mm. So with 25 mm increase in slump, water content we have to increase by 3%. So for 50 mm slump, the water value is 186 liter. If in place of 50 mm, if we consider 75 mm, which is 25 mm more than 50 mm, we have to increase the water content by 3% and it will become 191.58 liter. Similarly, if the slump value is 100 mm, so 50 mm more than 50 mm, so we have to increase the value by 6%. So it will become 197.16 liter. But for our particular problem, the slump value is 75 mm, so we will consider 191.58 liter for our particular problem. Now, we already know our water value, which is 191.58, and water cement ratio is 0.47. And obviously water cement ratio means weight of water by weight of cement. Weight of water we already know 191.58 kg or 191.58 liter, both are same actually. So weight of water is 191.58 kg. Water cement ratio is 0.47. So if I just simply calculate it, then the cement content will be 407.61 kg for 1 meter cube of concrete. So for 1 meter cube of concrete, we know our water 191.58 kg and cement is 407.61 kg. Now after we get these two value, we have to perform two different check. Now for this to check, we have to go to table 5 of IS 456. This is very important table, and this table is valid when the nominal maximum size of aggregate is 20 mm. If it is different, then what we have to do, that we will get from the additional video. But for our particular problem, we know our nominal maximum size of aggregate is 20 mm, our exposure condition is moderate, and our concrete is RCC concrete. So we have to consider this right side. This left side value, these are applicable for plain cement concrete. But our one is reinforced cement concrete, so we will consider this particular data. Now here, minimum cement content is 300 kg per meter cube, and our value was 407.61. So 300 is minimum, so it is okay. And maximum free water cement ratio is 0.50. Our base water cement ratio is 0.47, and this is the maximum. So again, it is okay. And minimum grade of concrete for moderate exposure is M25. And our problem is also for M25. So it is also okay. And now again, if we go for the check, here you can see that water cement ratio for our problem is 0.47. Maximum permitted is 0.50. So it is okay. Cement, calculated cement content is 407.61 kg. Minimum permitted is 300 kg. So again, it is pass. So our cement content is okay. Our water cement ratio is also okay. So now, after that, we have to go for air content. Now, this is also important. Our code prescribed 3 different value for 3 different nominal maximum size of aggregate. And you will get it from table 3. Our nominal maximum size of aggregate is 20 mm. And for 20 mm nominal maximum size of aggregate, the entrapped air in percentage is 1%. So 1% will be air, rest 99% will be rest. So 1% is already occupied by air, 99% is available for water, cement, and different type of aggregates. So we have total 1 meter cube of concrete. Now we know the weight of cement, which is 407.61 kg. Now by doing this simple calculation, we can get the volume of cement. Now we know that specific gravity equals to unit weight of solid by unit weight of water. Now what is unit weight of solid? Unit weight of solid is weight of solid by volume of solid, and here unit weight of water. So specific gravity into unit weight of water equals to weight of solid by volume of solid. So volume of solid equals to weight of solid by specific gravity into unit weight of water. Now what is the weight of solid? Weight of solid is 407.61 kg. Specific gravity 3.15 for cement, and unit weight of water how much? 100 kg per meter cube. So the volume of cement is 0.129 meter cube. So volume of cement is 0.129 meter cube. Similarly, the volume of water will be 0.192 meter cube. Volume of air is 0.01 meter cube, 1%, and rest will be all in aggregate. That means total 1 minus 0.129, 0.192, and 0.01. So it will be the volume of all in aggregate, which will be 0.669 meter cube. So 0.669 meter cube is the volume of all in aggregate. Now there will be some amount of coarse aggregate and there will be some amount of fine aggregate. Now how much amount will be taken by coarse aggregate and how much amount will be taken by the fine aggregate, that we have to calculate. And for that calculation, we have to go to table 5. Table 5 is actually the table of volume of coarse aggregate by volume of total aggregate. That means how much volume is coarse aggregate in total aggregate. Total aggregate is 100%. So how much is coarse aggregate and how much is fine aggregate? That we will get from table 5. Now this particular table is valid when the water cement ratio or water by cementitious material ratio is 0.50. If the value is different, then we have to do some modification. Now our nominal maximum size of aggregate is 20 mm and our zone of fine aggregate is zone 1. So zone 1 and nominal maximum size of aggregate 20 mm. So our value is 0.60. 0.60 is the value of volume of coarse aggregate by volume of total aggregate if the water cement ratio is 0.50, which is not our case. But if water cement ratio is 0.50, at that time the volume of coarse aggregate by volume of total aggregate will be 0.60. That means 60%. So 60% will be coarse aggregate, rest 40% will be fine aggregate. Now, if water cement ratio is 0.5, then coarse aggregate by total aggregate will be 0.6. But we have to do some modification if the water cement ratio is not 0.5. If the water cement ratio is not 0.5, then we have to apply a modification of minus plus 0.01 for every plus minus 0.05 change in water cement ratio. That means if water cement ratio decreases by 0.05, we have to increase the ratio by 0.01. So if water cement ratio is 0.45, that means 0.05 less, so it will be 0.01 more. If the water cement ratio is 0.4, 0.4 means it is 2 time change, 0.05 less, 0.05 less. So we have to increase the ratio of coarse aggregate by total aggregate by 0.01, 0.01. So it will be 0.62. If the water cement ratio is 0.55, which is actually 0.05 more than 0.5, at that time we have to decrease the value of coarse aggregate by total aggregate by a value of 0.01. So it will become 0.59. So by using the unitary method, if the water cement ratio is 0.47, that means 0.03 less from 0.5. At that time we have to use the unitary method and we will get our value of coarse aggregate by total aggregate ratio as 0.606. And why this particular value is changing? For that we can actually simply use the concept of specific surface area. And we know that if particle size is small, then more water is required to wet the surface. Now for a particular problem, if water cement ratio is less, that means water is less. And if water is less, then we can actually wet less amount of surface of aggregate. So if we want less amount of surface of aggregate to be wetted, at that time we have to use more coarse aggregate. Again, if I repeat again, if water cement ratio is less, water cement ratio less means water is less. And we know that if for a particular particle, if the surface area is more, if particle is finer, surface area will be more. And if surface area is more water is required to wet the surface. Now, if we have less amount of water in our hand, then we have to decrease the surface area. And decreasing the surface area means increasing the particle size. So when we have less amount of water, we have to increase the coarse aggregate percentage. And when we have more amount of water cement ratio, we have to decrease the coarse aggregate percentage. So this is the simple logic. Now this particular coarse aggregate by total aggregate ratio for our problem is 0.606. That means 60.6%. So what is the fine aggregate by total aggregate ratio? That will be rest. Coarse aggregate by total aggregate is 60.6. So fine aggregate by total aggregate will be 39.4. So this is the simple logic. Now we have to modify this value if the concrete is pumpable. If concrete is pumpable, it needs to flow smoothly through pipes without blockage or segregation. And for that, the internal composition of aggregates must be adjusted. So when concrete is pumpable, it have to smoothly flow through pipes. So what we do at that time? We decrease the coarse aggregate by total aggregate ratio by 10%. So normally the value is 0.606. If concrete is pumpable, we will decrease it by 10% and we will get a value of 0.5454. So what will be the fine aggregate by total aggregate ratio? It will be 1 minus 0.5454. So it will become 0.4546. So this calculation we have to do if the concrete is pumpable. If the concrete is not pumpable, at that time no correction, this type of correction is not required. And we can simply use this particular value of coarse aggregate by total aggregate, which is 0.606. So what will be the fine aggregate by total aggregate? It will be 1 minus 0.606. So it will be 0.394. Now we know the weight of cement, volume of cement, weight of water, volume of water, volume of air, and we have also calculated the volume of all in aggregate, which is 1 minus all this value. 1 minus the volume of cement, volume of water and volume of air. So the volume of all in aggregate is 0.669 meter cube, which we already calculated. Now, After that, we have to calculate the volume of coarse aggregate and the volume of fine aggregate. Now, we know the volume of coarse aggregate by total aggregate ratio as 0.606 and the volume of fine aggregate by total aggregate ratio as 0.394. So now if we simply multiply the volume of all in aggregate with 0.606, then we will get the volume of coarse aggregate. And if we simply multiply the volume of all in aggregate with 0.394, then we will get the volume of fine aggregate. Now, after we get the volume of coarse aggregate and volume of fine aggregate, we can simply calculate the weight of coarse aggregate and weight of fine aggregate. Previously, we have calculated the volume of cement from weight of cement by using one particular expression of specific gravity. Now, just by doing the reverse calculation, we can actually calculate the weight of coarse aggregate and weight of fine aggregate. Now, how we can calculate the weight of coarse aggregate? Weight of coarse aggregate will be volume of coarse aggregate into unit weight of water into specific gravity of coarse aggregate. Similarly, what is weight of fine aggregate? Weight of fine aggregate will be volume of fine aggregate into unit weight of water into specific gravity of fine aggregate. So, what is the weight of cement? Weight of cement is 407.61 kg. Weight of water is 191.58 kg. Weight of coarse aggregate is 1154.25 kg. And weight of fine aggregate is 699.6 kg. So now the weight of water is 191.58 kg because for water we know 1 kg equals to 1 liter. The weight of cement is 407.61 kg. The weight of fine aggregate is 699.6 kg. And the weight of coarse aggregate is 1154.25 kg, all for 1 meter cube of concrete. Now finally, when we are doing the construction, at that time the most important ratio is actually the ratio of cement, fine aggregate and coarse aggregate. And for this ratio, normally we take the weight of cement as 1. So we have to divide all this value with the weight of cement. So if we divide all this value with the weight of cement, then we will get this ratio. So 407.61 kg. If we divide the weight of fine aggregate by weight of cement, we will get the value of 1.72. And if we divide the weight of coarse aggregate by the weight of cement, we will get the value of 2.83. So final ratio will be 1:1.72 is to 2.83. And water cement ratio is the weight of cement by weight of water. And it is 0.47 for our particular water cement ratio. Now, this is not the end of our calculation. There is one more step called field correction. It is done on the day of casting because it depends on the actual field condition. Normally, on a dry day, coarse aggregate remains dry and it absorbs water from the concrete mix to reach saturated surface dry condition. In SSD condition, inside pores are filled with water, but the surface is dry. This is the standard condition used in mix design. So if the coarse aggregate is dry, it will absorb water from the mix. Therefore, we must add extra water. Now for the fine aggregate, it normally contains moisture. If the moisture is more than its absorption, it will give water to the mix. So in that case, we must reduce some water. So remember the simple logic. Dry aggregate absorbs water, so we have to add more water. Moist aggregate gives water, so we have to reduce the water. Now, let us see the conditions of aggregate. First, this is bone dry aggregate. Bone dry means it is completely dry. Now this is air dry aggregate. Air dry means some moisture is present inside, but the surface is dry. Third one is the saturated surface dry condition. It is fully filled with water inside, but the surface is actually totally dry. This is the ideal condition for concrete mix design because normally we consider that the water that are present inside the aggregate that will not take part in any type of cement hydration. If there is some water outside, it will react with cement. But if there is water inside the pore, it will not take part in any type of reaction. So saturated surface dry is taken as the standard condition. And this is moist condition. For moist condition, some moisture will be outside the aggregate. So if there is some moisture outside the aggregate will actually donate this extra moisture to the concrete mix. Now, suppose from the lab testing, we find out that water absorption for coarse aggregate is 3%. So coarse aggregate will absorb 3% of its own weight. 3% of coarse aggregate comes out to be 34.63 kg. So we must add this extra water to the mix because the aggregate will absorb this much amount of water. Now for the fine aggregate, suppose it has 2% free moisture. So sand will give 2% water to the concrete mix. So this amount of water must be reduced. 2% of fine aggregate is 13.99 kg. So this much amount of water will come from the sand itself. So we have to reduce this much amount of water. Now we do the final correction. Cement remains same. Corrected water will be original water plus water absorbed by coarse aggregate minus water from fine aggregate. So the corrected water will become 212.22 kg. Fine aggregate also changes, 699.6 kg plus 13.99 kg. So it will become 713.59 kg. Coarse aggregate also changes, 1154.25 kg minus 34.63 kg. So the corrected coarse aggregate will become 1119.62 kg. So this is how field correction is done in concrete mix design. Now after that, we will prepare the concrete mix. And when we will prepare the concrete mix, our first work will be to measure the slump value. Normally, the slump we get may not exactly match with the value assumed in our design. For example, in our design stipulation, the required slump is 75 mm. But after preparing the mix, the slump we obtain may be different. So in that case, we need to adjust the mix. The best method is to use a chemical admixture. By slightly changing the dose of admixture, we can achieve the required workability without changing the water-cement ratio. But suppose no admixture is available, then what we can do? Let us take a simple example. Suppose the required slump is 75 mm, but for our trial mix, we obtained only 50 mm. That means the concrete is stiff. One simple solution is to increase the water. But if we only increase water, the water-cement ratio will also change. And this is not desirable because water-cement ratio controls the strength of concrete. So what is the correct approach? We should keep the water-cement ratio constant. If we increase water, we must increase cement also proportionally so that water-cement ratio remains constant. And if we decrease water, we must decrease cement in same proportion so that the water-cement ratio also remains same. This way, the water-cement ratio remains unchanged. In our problem, the water-cement ratio is 0.47. So we must maintain this value. But we can adjust the quantity of water and cement together until we get the required slump of 75 mm. The adjustment is normally done during the trial mix stage as recommended in our IS code. Now this is another important step when we are doing the construction. Now all this calculation is not very required when we are doing a problem in exam. Now previously modification or this modification all are required when we are doing construction. At construction site, all these concepts are actually required. Now for our particular problem, we know that our water-cement ratio we have considered was 0.47. This is our base trial. But it may happen that after we prepare done all the mix design calculation and then we prepared the concrete, and after 28 days of concrete cube, we may find out that the strength of concrete is not coming same to our target mean strength. It may be more, it may be less. So what we have to do? Because when we have started our problem, we assumed the water-cement ratio based on some graph which are given in our IS code. But that is not our actual graph. The actual strength versus water-cement ratio graph for our problem can be different. So what we have to do? At that time, our code is saying that we have to do 2 more trial based on plus minus 10% water-cement ratio. So for one condition, our water-cement ratio is 0.47. So plus 10% is almost close to 0.52 and minus 10% is almost close to 0.42. So we have to do all our calculation for these three mixed proportion, and then we have to prepare some graph of water cement ratio versus strength, and from that we can actually get the correct amount of water cement ratio. So what are the different steps? I am just elaborating it in the next slides. So now suppose for our problem the base water cement ratio is 0.47. Now this is trial 1. Trial 2, we are increasing the water cement ratio by 10% and it will become 0.52, close to 0.52. And trial 3, we have to reduce the value by 10%. So it will become 0.42. Now we cannot consider the value 0.52 because it is written, it is clearly mentioned in our IS code that maximum water cement ratio for moderate condition is 0.5. So for trial 2, we can consider the water cement ratio as 0.5. So we will do our mixed design calculation for these three different water cement ratio. First we will do the calculation for water cement ratio 0.47. Then we will do our mixed design calculation for water cement ratio 0.50. And then we will do our mixed design calculation for water cement ratio 0.42. And after doing all this calculation, we will prepare three different set of concrete. And after we prepare three different set of concrete, we will do the casting of concrete cube. And after the casting of concrete cube, we will leave it for 28 days of curing. And after 28 days of curing, we will measure the strength for these three different water cement ratio. So after that, when we will get the strength of concrete for these three different water cement ratio, then we have to prepare one water cement ratio versus strength graph, and it will look something like this. Now this graph is little bit difficult because when we are preparing this type of graph, there may be huge error when we are doing the card fitting. So in place of that, we can simply use the graph of cement water ratio versus strength. So in place of water cement ratio versus strength, it is better if we use cement water ratio versus strength, because water cement ratio versus strength graph is actually curvy in nature, but cement water ratio versus strength graph is actually linear. So we can go for this particular graph. Now our first water cement ratio is 0.47. For that, suppose we got the cube strength as 32 Newton per millimeter square. Second trial, the water cement ratio is 0.50. For that, suppose we got the cube strength of 30 Newton per millimeter square. And third water cement ratio is 0.42. For that, suppose we got the cube strength of 35 Newton per millimeter square. So we will calculate the cement water ratio, and based on this cement water ratio, we will plot the graph of cement water ratio versus strength of concrete. Now these three will be the point, and we will connect it by one straight line. Now best thing is if we use Excel sheet. If we use Excel sheet, we can actually get the proper trend line, which is actually the best fit line. And from the best fit line, Y is the strength and X is the cement water ratio. So if we just get the simple expression of best fit line, then putting the value of Y as our target mean strength, we can get the actual value of cement water ratio. Now we can also do this in hand also. If there is no availability of Excel, at that time we can simply add one straight line, and from our target mean strength, which is 31.6, if we draw one horizontal line, it will cut this particular straight line in one point, and from that point, if we draw one vertical line, then it will give us the actual cement water ratio which is required for our particular problem. So the actual cement water ratio here is 2.11. So the corresponding water cement ratio will be 1 by 2.11, which will be 0.473. So this value 0.473 is our final water cement ratio. This value will be used for the final concrete mix design. Using this ratio, we will finally calculate the cement content, the fine aggregate, and the coarse aggregate proportion. So this is how concrete mix proportioning is done according to IS 10262 2019. If you have any question, you can write them in the comment section. Thank you for your attention. Thank you.